Hello everyone. In this video, I'm going to talk about the different types of nonlinear problems in structural analysis. The first type of nonlinearity I would like to talk about today is material nonlinearity. So taking this bar, for instance, and let's say we subject to uniform tension. We put it, and eventually the bar is going to, if it is made of steel, it's going to yield. So it would have a plasticity, which means that the stress-strain curve will start to deviate from linearity, and if we unload it, it follows usually the original stiffness. The second type of nonlinearity, material nonlinearity, is damage. So there could also be microcracks developing around the bar, such that if we unload this bar, so it will initially deviate from linearity, of course, but if we unload this bar, it would follow the sort of a secant stiffness path to the origin. So that happens because all the microcracks are degrading the stiffness of the material, and when you unload, they are gradually closing up. And eventually, if you pull it hard enough, in either cases, you will have a fracture. This means that the stress will start to go down as you load it further, and depending how on the material property, especially the fracture toughness, the curve could have a sudden drop, or it could degrade gradually if it's tougher material. So more on this damaged fracture in the later part of this course. And the essential takeaway on this slide is that when we have material nonlinearity, the relationship between tau, which is the Cauchy's stress, and epsilon, which is the strain, is no longer linear. So we no longer have a constant constitutive matrix to relate the two. The material behavior is no longer classified as linear elastic. The second type of nonlinearity that is commonly experienced in aerospace engineering is called geometrical nonlinearity. This type of nonlinearity is characterized by a big change of the geometries. Remember that the linear FEM, we never make the distinction between the initial configuration and deformed configuration, but here under geometrical nonlinearity, we can no longer do this. Under geometrical nonlinearity, there are two particular cases. The first case is when we have large displacement but very small strain. This is the case with a cantilever beam bending, for instance. When we have a cantilever beam and let's say we want to bend it under a force downward, the beam could deflect by a large amount, and you could do this experiment yourself. But if we look at each segment of the beam, each material point is actually experiencing very small strain, so it still remains in a linear elastic regime, which means that if we remove the force, the beam would go back to its original configuration without any damage or material nonlinearity experience. So if we look at a material point, it undergoes large displacement and large rotation, but there's not much change in terms of the length of the fiber segment or the angle between the different fiber segments, so which means that the strain at this material element is actually very small. However, it's still nonlinear because if we plot the force versus displacement, until a certain point, this curve would start to deviate from nonlinearity, and this nonlinearity is not caused by any material damage or plasticity, but it's entirely caused by the fact that we are having a large change in the geometry of the body. In case 2, we would have both large displacement and large strain. This is the typical case with rubber. If we pull the rubber block, we could pull it to a very large extent. So if we measure the stretch, lambda, stretch is defined as the current length of the rubber divided by the initial length of the rubber. So the stretch could go up to 5 times. And in this process, the relationship between sigma, which is stress, and lambda, which is stretch, is nonlinear. If we look at each material element within this rubber, from here to here, it's experiencing both large displacement and rotation together with it. And also, if we look at the fiber segments, they are changing considerably in terms of length and also in terms of their relative angles, which means that in this case, we have both large displacement and large strain. The third class of nonlinearity is contact. So taken, for example, a rigid ball contact a soft medium. Right? The ball is subject to a force F downward, and it would come into contact and it would indent into the soft body, and the radius of contact, which is A, would start to increase together with the depth of indentation. This is nonlinear because if we plot the radius of contact versus this depth of indentation, it's a nonlinear function. And more importantly, if we plot the force required to indent to a depth of d, is a nonlinear function as well. So basically, the contact area and force are nonlinear functions of displacement.